Okay, welcome everyone to my continuation of what are my favorite theorems. Very biased collection. Well, it's going to be a very biased collection of favorite theorems. I would like to do two videos actually. This was of course just one. You just clicked on one video, so you only get one. On fractals and inverse fractals. So inverse fractals are kind of not as well known as fractals, but they kind of appear more in combinatorial setups, while fractals come really from analytic setups. That's kind of an interesting kind of dichotomy. Dichotomy, is that the right word? So two sides of the same coin. Yeah, and the fractal is really about zooming in, and the inverse fractal, as you might have guessed now, this is a really ugly circle. The inverse fractal, as you might have guessed now, by now, is like zooming out. But anyway, today we'll stay with what is a fractal, and I'm trying to motivate a little bit what it is without really defining it. I will define it, I think, but it is kind of a little bit of a strange definition. I kind of more motivated what it really is in terms of what its historical development, because they're actually quite old, actually, and kind of roughly what they are will be in some form of a definition in quotation marks. And then the inverse fractals are somewhat easier to define because they're combinatorial gadgets. Well, we'll see them not in this video, but eventually. So the history of fractals, part 1. As far as I can tell, I mean, there were some preliminary kind of, for example, Leibniz apparently already studied fractals, but then kind of got confused whether there's some self-similarity in the line itself, because the line is self-similar to one of its pieces, but the line is not a fractal. Anyway, so there was some prehistory, but essentially it starts with Weierstrass, so it's 1850-ish. And yeah, roughly what I would like to have in mind is a fractal that's something that is self-similar in some way or form. And another definition of a fractal, if you want to call that a definition, is a nowhere differentiable function. And this is where Weierstrass entered the game. So kind of historically, it's kind of analysis, calculus is like really old, Leibniz and friends, Newton and Leibniz and friends. But later, like with Cauchy and other people, it came into this epsilon delta thing that you might have seen, which we could call a rigorous version of calculus, whatever you want. Let me just call it the epsilon delta thing that you might have seen, and people tried to come up with very precise statements. In particular, can you have a function that satisfies A but not B, something like that. And Weierstrass was thinking about the problem of having a function that is everywhere continuous but nowhere differentiable. So what I should have written is probably nowhere differentiable function but everywhere continuous. Otherwise, it's a little bit boring. So I want some function like in the picture above here. So why is it nowhere differentiable? Well, let's say you want to kind of write down a tangent somewhere. That's what it means to be differentiable. You try to have something like this, but if you zoom in, there will be more and more of those little. It's kind of exactly, if you zoom in, you will more and more of the little zigzags, and if you zoom into zigzags, you will see more and more zigzags. So whenever you try to put a kind of, well, this is a bad picture. Whenever you try to, put a little tangent at a point, but you then zoom into the point, like it's done here, then you will see another bump, and you can try to put in that tangent a little bit, but then you zoom in into this little bump, and you see more bumps, and so on and so on. So it's kind of a self-similar structure. So everywhere continuous and nowhere differentiable function, that's what it's called, the Weierstrass curve, and this was kind of the first example of what you might consider a fractal, because as I said, as you zoom in, you see more and more bumps. You could think of a little bit of an easier thing, if a sine function, for example, but it's not really a sine. Whenever you zoom in, there's a little bit of a tiny sine added to the sine, and in each tiny sine, there's a little even tinier sine added to the sine, so it goes up and down. You get the point. It's kind of the self-similar story. And you can't really put a tangent on such a curve. And this is where it started, like in the 1850-ish, kind of coming really from analysis, and that's where it came from. And much later, so like 50 years later, that's actually not that much if you think about 1850, where everything progress was much slower. So nowadays, if I have a question, I ask Dr. Google, and what would you have done in 1850? You might have walked into the library, that already takes a long time, trying to search a book, and you can't just use some kind of AI to find the book. And if you have a question, you nowadays you might just email someone, and at that time you just wrote a letter, which then was sent. It's terrible. Things were very slow, so maybe 50 years is not that much. But history part 2 is now the geometric definition. So really it came up as this idea. I think this one was one of the first one, the Koch snowflake. It comes out as an idea of iteration. You start with a triangle, and then along a triangle at each of its sides you put another little triangle. It's kind of an iteration process. Well, step 1, step 2, and now step 3. At each triangle side you put another little triangle, and so on. And what you get is kind of a strange thing with a lot of, again, kind of the same type of pattern with a lot of bumps somewhere. And yeah, there will be a non-differentiable curve, which is still kind of continuous, but it kind of has a more geometric definition, like in this iteration process. You try with some geometric object, you do some operation to it, and then you get another geometric object to which you repeat the operation. Like here in my example, you have a triangle, and you put a triangle on the triangle, and then you put a triangle on the sides of the triangle, and you just keep on going, and then the fractal is the limit of that process. And that was this definition of Koch and other people, which might be the most famous one by now, which you might have seen at some point, kind of those, because it's kind of really nice and easy to describe. The one where it then really appears, like if you think about maybe the most famous fractal for some reason, is the Mandelbrot set. And it really appears in dynamics. Essentially, whenever you have some system, some dynamical system, there will be some chaotic behavior, there will be some stable behavior, and the border between them tends to form a fractal as well. Here's something coming from Newton's method. So Newton's method for a certain polynomial, which is not too difficult, x cubed minus 1. And the 3 roots of the polynomial give you kind of a stable behavior, and they're the 3 colors. And you can see this fun pattern of having green and green, blue, this is a nice blue, red and red, blue and blue. Like it's a 6-fold around each point, and there will be more points which has the same set pattern, and if you zoom in, there will be more points with the same pattern, and so on and so on. Kind of the dynamics definition is kind of this border between chaos and order. So essentially here, if you do it in this region with starting values in this region, then everything will be nice. If you do it in starting values in the white region, then everything will be pretty chaotic. So it's kind of this border between the two. Similarly, so those are called Julia or Fatou sets, depending a bit who you ask, and one of them is kind of the opposite of the other. One of them is the order one, and the other one is the chaos one. And then kind of my theorem, my favorite theorem of all time, that this little plant here, which is very, very, very tasty, by the way, and this little guy here, which I call a brain, I guess, they actually have the same dimension. It's kind of a fun result. I'll explain in a second what dimension is. So people in this setting of fractals, after this picture here was kind of known, or kind of emerged, Hausdorff mostly was asking this question of, can we associate a nice notion of a dimension to those spaces, which kind of makes intuitively sense. They're a little bit kind of bigger than whatever. The Koch snowflake is actually a line, but maybe it's a little bit bigger than a line, so something like that. We'll see that in a second. And yeah, so the definition of a fractal that Mandelbrot then proposed is roughly along the form is, well, it's a kind of set where the Hausdorff dimension is bigger than the topological dimension. So then the Hausdorff dimension, the fractal dimension, is bigger than the fancy dimension. The fractal dimension is bigger than the intuitive topological dimension. I'm going to repeat both of them in a second. And yeah, so that really popularized, well, not really. What really popularized fractals was the age of computer-generated pictures, because before that, people, I mean, what can you do by hand with fractals? If you think of them as like an infinite process, what can you do by hand is not much. What you can do by hand is something like this, and then more and more fancy fractals. So this is clearly a computer-generated picture. More and more fancy fractals emerged. Here's one of my favorites. It's kind of so simple. The H picture. So you draw a little box where you put in an H. So an H was filling this box, 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 this box, and this box, which gives you an H. But now you can think of every filled box again. I can zoom in again and can think of it as again as a picture that you can draw it as an H. So we get this H and an H and an H and an H and an H, whatever. And it looks like an H. What a surprise. So you can generate like a zillions of pictures using computer nowadays. That's why those fractals became very, very popular. But they really came out of some analytic thinking, depending a little bit on your flavor, really just nowhere differentiable functions, or maybe this border between chaos and order. So what is this Hausdorff dimension? Well, it's nowhere on the slide because I decided it's too annoying to write down, where actually the box dimension, what is called the box dimension, is easier to define. So it is a little bit of a zoo of dimensions in this case, because it's the point is like the intuitive way to define a dimension as the number of coordinates you need to describe something. Maybe is not the right thing for fractals, so they are slightly different. So there's a list of different dimensions you can associate to a space. The Hausdorff one is the most common one, but it's also a little bit annoying to explain. The box dimension is almost always, in almost nice examples, the same as the Hausdorff one, but it's a bit easier to explain. So I will do that. And clearly the box dimension is not on the left, it's clearly on the right. Otherwise it doesn't make sense. So topological dimension is kind of nice, it's on the left. So here, left and right. And Hausdorff dimension, the almost Hausdorff dimension, the box dimension, is on the right. And it works as follows. The topological dimension is the minimum n that is needed to kind of cover all points, so that every point is in no more than n plus 1 covering sets. So if you think about a circle, you could cover it with those little, whatever they're called, blobs. Let me call them blobs. I like the name blobs. You cover them with those little blobs, and no point is in more than 2 blobs. And the points here at the intersection, at the right intersection, they're in 2. And otherwise it's in 1. So this guy has dimension 2. And n plus 1 covering set, so it has dimension 1. Right? N plus 1 is 2. So 1 plus 1 is 2, so it has dimension 1. So this is supposed to be a 1. 1 plus 1 is 2. Let me try again. This is terrible. So 1 plus 1. That's a very easy calculation. I should be able to do that. So give me a second. 1 plus 1 equals 2. Yeah, it makes sense. So this one is a dimension then. So it's dimension 1, as a circle should be, right? If you do the same for a square, so for a filled out square, no matter how you wiggle it, you will always find points, like in here, this one here, these are in 3 different coverings. So this one should be of dimension 2, as a square should be, I guess. And yeah, so that's the intuitive definition. And if you just think about it through, what happens for the squares of the right dimension and whatever, everything will be of the kind of right dimension. And this box dimension is very similar, but then a little different. It's trying to approximate this Hausdorff dimension, which was defined historically first, but it's a little bit shitty to write down, so we're not going to do it. And the Hausdorff, the box dimension is just defined as, well, let's say you want to cover here the coastline of England, so you cover it with squares of lengths, or with boxes, that's where it comes from, of side lengths epsilon, and you take this limit of epsilon to 0. Yeah? So to make the boxes smaller and smaller, and you count how many boxes you need, and that's kind of the dimension. And if you do that for the coastline of England, then you get something like 1.3-ish. And if you do that for the Koch snowflake, you get whatever it is, some log of something. So that's the Hausdorff dimension. The fractal is where those two don't agree, like for the coastline of England, where you get 1 for, because it's just a circle, for this dimension. The Hausdorff dimension is approximately, of course, because it's a real world problem, approximately 1.3. Anyway, so next time I would like to talk about the inverse process, which comes from combinatorics and not from number theory combinatorics, some more discrete things, and not from analysis, which I kind of feel like is pretty cool, and kind of the inverse process. Here we had the zooming in, and later we will have the zooming out. Anyway, I hope you enjoyed this video, and I also hope to see you next time.